Hi, welcome back to Keys Precalculus. This is the continuation of section 1.3 that we began in class today. We ended up with talking about the increasing and decreasing intervals of functions. I would like for you to pause the video for a minute and look over page 32 at the definition and the example 4, and then I want you to go to page 39 and try number 20. I recreated the problem here on the screen, but I want you to try number 20 on your own and then come back and see if you got the same answer that I got, and we will talk about it. But don't forget that when we're talking about increasing and decreasing intervals, our intervals are the x values. It's where the graph or the y values are increasing and increasing or decreasing or remaining constant as we move along the x-axis. So go ahead and pause your video and then come back and see if you got the same answers I did. Okay. They gave you the graph, they gave you the equation, which was f of x equals the square root of x squared minus 1, and they drew the graph for you. If they hadn't drawn the graph for you, you could have used your graphing calculator to graph this function, and you would have seen the same thing that they gave you and that I drew here. For these kinds of problems, go ahead and use your graphing calculator to look at the pictures if they don't give them to you. Look at the graphs of the functions if they don't give them to you, because I don't expect you at this point to be able to recreate them easily. All right, so anyway, this particular graph of the function f of x equals the square root of x squared minus 1 is decreasing from negative infinity to the number negative 1 on the x-axis, along the x-axis. I wrote out parentheses for both of these, even though there is a closed circle at negative 1, because when you get to the point negative 1, it is no longer decreasing. It just is. So it's decreasing up until that point, but at that point it is negative 1. The graph is increasing from the point 1 to positive infinity, when x is 1 all the way to positive infinity. And again, even though it's a closed circle on the graph, it's not increasing at 1. It begins increasing just after 1 and then continues on to infinity. The graph does not have an interval where it remains constant. Yes, the y values are the same at x equals negative 1 and x equals positive 1. However, it doesn't remain the same between those 2 points. So there's not an interval where it remains constant. So your answers would be what I have up here if you were to get it correct. The very last thing we talked about in class was the relative minimum and the relative maximum values of a function. I would like for you to look on page 33 at the definition and then look at example 5. At this point, you're not going to have to graph these by hand to figure out what the relative maximum and minimums are. What I'd like you to do is use your graphing calculator and use the trace function or the step function or whatever it is for you to get to that point to pick where the relative maximum and maxima and minima are on your graph. So you can pause this video in a minute, look at page 33 and page 34, and I want you to study examples 5 and 6 and practice them on your graphing calculator, and then come back. Okay. That your book does not cover extensively, but they expect you to know because you learned it in Algebra 2, is the end behaviors of functions and how they behave, how a function behaves, and in fact, in other words, how the y's behave as x approaches negative infinity and x approaches positive infinity. So we're going to talk about that here, and I put the 4 examples up here. Hopefully this jogs your memory from what you learned in Algebra 2. But like this green one here, as x reads from negative infinity to positive infinity, or we read from left to right, this dark green function is obviously the graph of a line, and it also goes from negative infinity to positive infinity. It rises. So as you read from left to right, you can see that this graph increases, or the y values increase, or you can say that it rises. Same thing with this light green graph. Yes, somewhere here in the middle, you've got some relative maximum and relative minimum points. However, if you zoom out overall, this graph is an increasing function. Its in behaviors increase. In other words, as x goes to negative infinity, y is also going to negative infinity. And as x approaches positive infinity, y is also approaching a positive infinity. So when this happens, when you've got a graph where as x goes to negative infinity and y goes to negative infinity, its in behavior, and as x goes to positive infinity and y goes to positive infinity for its right side in behavior, then you know that this graph has to be a graph of a function that has an odd power. That means its leading coefficient determines the power of the function. It's the highest exponent of the x variable in the function. So it has to be odd. So the green graph, now these graphs are not, these equations, these functions are not exactly the equations of these graphs that I drew. I just made them up, okay? But I just wanted to show you that, for example, here this dark green function is a linear function and its power is 1. Its leading coefficient is greater than 0. Therefore, it rises. The slope is positive, so it rises. But you could also have a power of, let's say, 3 or a power of 5 or a power of 7. It doesn't matter. As long as you've got an odd power and the leading coefficient is 1, the graph is going to rise at its over time, at its in behaviors. Okay? But if you look over here at the blue ones, you're going to see that these graphs fall. Another example, this is linear. So I put negative 2x plus 7. That is not exactly the same function or equation for this graph, but I just made it up. Or you could have something like f of x is equal to negative of x plus 2, all raised to the third power. Again, it's not the same. It's not the equation for this light one, but it's still an equation where you have an odd power. The power of this light blue one is 3, the power of this dark blue one is 1, and as x approaches negative infinity, y approaches positive infinity, or as x approaches positive infinity, y approaches negative infinity. When this happens, when overall the graph is falling, then your function is an odd-powered function whose leading coefficient is less than 0, or its leading coefficient is negative. In other words, odd-powered functions are either going to rise or fall. Even-powered functions, however, either open up or open down. Even-powered functions example would be a parabola like x squared, or a graph that has an x to the 4th to it, or an x to the 6th to it, where its leading coefficient, or excuse me, not leading coefficient, its leading term has got an even power. If the function has an even power and its leading coefficient is greater than 0, it's going to open up. In other words, as x approaches negative infinity, y is going to approach positive infinity, and as x approaches positive infinity, y is also going to approach positive infinity. Now, yes, the graph will decrease over an interval until it starts increasing, but its in behaviors are as x goes to both negative and positive infinity, y is going to approach positive infinity. But if you look here at this purple graph, you're going to see that these are also even-powered functions, but as x approaches negative infinity and positive infinity, y is going to approach negative infinity in both directions. In other words, they're going to open down. Yes, the graph increases to a maximum and a relative maximum, and then it decreases, but over time, it's going to always, it's opening down. So even-powereds either open up or down. Depending on what their leading coefficient is, they will open down if the leading coefficient is negative. They will open up if the leading coefficient is positive. Odd powers will rise or fall over time, depending on what the leading coefficient is. I hope this makes sense. You might need to go back and study this in your Algebra 2 book, or you can come back here and or pause this video and look at it and see if you understand what I'm talking about. Think about it, dwell on it. The next thing we're going to do is we're going to talk about the graphs of piecewise functions and step functions. I'm going to start with the piecewise function because we talked about that last week in class, and I'd like to just go ahead and practice graphing that with you now. If I were to give you this graph and I say, let's graph by hand the first piecewise function, the one with the blue and the purple equations in it, let's go ahead and practice doing that together. You will notice both the blue function and the purple function are linear, but together they create one function that's piecewise. So the way I'm going to graph it is I'm going to graph it like I would do any line. I will find my slope and my y-intercept, but in order to do that, I've got to, well, it's already solved for y. F of x is y. So I can look here and I can see that my slope is, in the blue one, my slope is 2 or 2 over 1. And my y-intercept is 3. But I'm only going to graph it for all the values of x that are less than or equal to 1. Now my y-intercept is the point 0, 3. Don't forget, because on the y-axis all the x values are 0. So that means x is less than 1 here, so I know that my y-intercept is going to cross the y-axis here at the point 0, 3. Okay, and its slope is rise 2, run 1. And I can do that up until the point where x equals 1, and it includes 1. That's really not enough, so I'm going to fall 2 and go left 1, fall 2 again, and go left 1. And let's see if I can draw a straight line on this. I'm going to pretend like I can draw. Oh, well, it clicked to straight. Okay, on this graph. So that is the first part of this piecewise function. It's the blue part. There's a second step to this for all the values of x that are greater than 1. So what I'm going to do over here is I'm going to find the slope of this one. The slope here is -1 or -1 over 1. And my y-intercept would be positive 4. Now, that means in the y-intercept that my x is 0, and that's not greater than 1. So I'm not going to be crossing the y-axis at positive 4. But I'm going to put a little ghost point right here, just so I can get my slope going. Okay, my slope is going to be from this point at y equals 4. I'm going to go down 1, right 1. Does it include this point? No, it doesn't. But that's where it starts, because I've got to have my values of x greater than 1. I can't include it. If I were to color this in, I wouldn't have a function anymore, because then I would have 2 values for 1. But it doesn't include it, so I can do an open circle. And then I can go down 1, right 1, down 1, right 1, down 1, right 1. So now I've got a graph here with a negative slope and but an open circle at 1 to show that it does not include that number, but it approaches it. And this does pass the vertical line test. So I have just graphed a piecewise function by hand. I would like for you to pause the video and try to graph the second one that I've listed here, the pink and green piecewise graph, on your own paper, and then come back and see if you got the same answer that I did. Okay, so look carefully at my graph and compare it to yours. I made my scale every single little interval here at 4 instead of at 1 or at 2, because if I would have made it any other way, it would not have fit on this particular graph. You can change your scale as long as you mark it. Okay, so you can see that this is a function because it includes the point -4, 2 on the pink graph, but it does not include the point -4, -12 in the green graph. It's an open circle. Both parts of it rise. Both parts of the graph rise. So overall it's a rising function, but each piece of this graph is a different line, or a part of a different line. Okay, so that's how you graph piecewise functions by hand. Now we're going to look at a step function. This may appear to be a piecewise function, but it's not. It's a step function. This one is called the greatest integer function. And what it means, it's the greatest, this function is, the y is the greatest integer that is less than or equal to x. And it has an infinite number of breaks or steps. one at each integer value for x. Its domain, all of its x values, are only going to be, well, excuse me, I'm sorry, I said that wrong. The domain are all real numbers, because the domain goes along the x-axis. Okay, but its range is only going to be the integers. And don't forget, the integers are the whole numbers and their opposites, or their negatives. So it's be like 0, 1, 2, 3, 4, 5, and then -1, -2, -3, and so forth. So the domain are all real numbers. The range are all the integers. And as you can see over here on the graph, it is a function because it would pass a vertical line test. Because every time I'd hit a closed circle here, I go down and it hit an open circle there. And so let's see if we can figure out how this works. What this means is if, what is y if x is -1? So what is the greatest integer, the integer that's closest to -1 that is less than x or equal to x? Well, -1 is an integer. And if your x is an integer, then your y is also going to be that integer, because it is either going to be that integer or the integer that's the closest integer to it that's less than x. And in this case, because x is -1, y is going to be -1. But here, so here on the graph, I would plot the point -1, -1. It would be this point right here. And then if x was like -0.5, it would also be -1, because that is the biggest integer that's less than x, which would be -1/2. Okay, but if x is 0, well, that's an integer, y would be 0. But here, x is 1/10 in the next problem. So that's a fraction that's a little bit bigger than 1. So what is the closest integer, the greatest integer that's the closest one to 1/10 that is either less than or equal to 1/10? Well, it's not 1 because 1 is bigger than 1/10. It has to be 0. Do you see here on this graph? If I were to move x to 1/10, y would be 0, because 0 is the closest integer to 1/10 that is not bigger than 1/10. So when x is 1/10, y is 0. When x is 1.5 over here, I keep losing my point. So x is 1.5, so it'd be 1.5 right here. What is y? Well, we can jump up and see right here y is 1. Well, why is that the case? Because 1 is the closest integer to 1.5 that's not bigger than 1.5. So my x value here would be, or my y value here would be 1. So when x is -1, y is -1. When x is 1/10, y would be 0. When x is 1.5, y would be 1. I would like for you to pause the video and try these next 4 purple problems. And when you come back, I will have the answers. Okay, check your answers and see if you got the same thing I did. When x is -2.5, the closest integer to that that's not bigger than 2.5 is -3, so y would be -3. When x is -3/4, that's greater than -1. The closest integer that's closest to it is -1. The integer that's closest to it that's not bigger than -3/4 is -1. When x is 6, y is also 6 because that's an integer. When x is 15.5, which is the same thing as 7.5, the closest integer to that doesn't go over it is 7. Do y'all see that? This is on page 35 of your book. We did the examples that are there, but you can read it, study that, study this, just to see that you have an understanding of what the greatest integer function is. It is not piecewise, it is a step function, but it is still a function. Okay, the last thing we're going to talk about is even and odd functions. The last thing in this section that we're going to talk about is the even and odd functions. I'm looking at page 36 and 37 in your book. I tried to recreate the graphs that they put on page 36 for you. Just pardon my drawing. I tried to do the best I could drawing it on here. But let's go ahead and talk about what these are. Okay, if you look at this green graph right here, you will see that it is a parabola and that is symmetric about or relative to the y-axis. or it says with respect to. So this green parabola here is symmetric, or you could say there's a mirror along the y-axis and it's reflected across it. I write symmetric about the y-axis. The book says symmetric with respect to the y-axis. It means the same thing. Okay? But what this means is for every xy on this graph, so like for example this xy here, which is the point 3, 1, there's going to be a negative x, or the opposite of x, but the same y. So there'll be the point negative 3, 1. If I have the point negative 1, 1 here, then it's going to be the point 1, negative 1 right here. And there's going to be a point negative 1, negative 1 right here. So if it's symmetric about the y-axis, for every xy you have, you're going to have a negative xy. If a graph, the graph of a function is symmetric about the origin, that means that there's no really mirror. I guess you could say there's a little mirror like right here. But what it means, because you can't, it's not reflected across the x, it's not reflected across the y, it's reflected with respect to the origin. That means that for every xy you have in a graph that is symmetric about the origin, you're going to have a negative xy, a reflection of both coordinates being the opposite. So if I have the point 2, 1 here on this graph, then if it's symmetric about the origin, then I'm going to have the point negative 2, negative 1 on this graph. If I have the point negative 2, negative 3 on this graph, then I'm going to have the point 2, 3, which I didn't draw it very accurately, but the point 2, 3 on this graph. So if a graph is symmetric about the origin, then for every xy value you have on the graph, you're going to have a negative x, negative y on the graph as well. Now let's look at a graph that's symmetric about the x-axis, or symmetric with respect to the x-axis. Here, I can see that this blue thing is not a function. It does not pass the vertical line test, does it? Nope. But it is still symmetric about the x-axis. That means for every xy point I have here, I'm going to have an x, negative y. So let's say that this was the point 0, 1. Then I'm also going to have a 0, negative 1. Or let's say this is the point 1, 1.5. Then I'm going to have the point 1, negative 1.5 on here. So a graph that's symmetric about the x-axis or with respect to the x-axis means it's reflected across the x-axis. For every xy you have, you're also going to have an x, negative y. So what does this have to do with even and odd functions? Well, every function that is symmetric about the y-axis is considered to be an even function. That means for every xy in an even function, there's going to be a negative xy in that function as well. Or the way that the way that we define it is a function f is even if for every x in the domain of f, f of negative x is equal to f of x. So in other words, if I were to substitute a negative x in for x and simplify it, I would get the same thing I started with, f of x. We'll do an example in a minute or two so you can see what I mean by this. Okay, so if a function is even, that means for every x in the domain of that function, I'm going to have for every x in the domain of that function, f of the opposite of x is equivalent to f of x. So for every xy, I'm going to have a negative xy. If a function is an odd function, that means it is going to be symmetric about the origin. In other words, for every xy in my function, I'm going to have a negative x, negative y. Or, if we're going to give the definition to it, I'm going to say a function f is odd if for each x in the domain of f, f of negative x is equivalent to the opposite of f of x, or the negative of f of x. That means if it was negative, it will be positive. If it was positive, it's going to be negative. Okay? And then you've got functions that are neither one. If it's symmetric about the x-axis, it is symmetric, but it's not a function, so it can't be either or odd. Or if you've got a function that looks like this right here. It's a parabola, so you think, oh, it's symmetric about, well, yeah, it's symmetric about its axis of symmetry, if I could draw a straight line here, but it's not symmetric about the y-axis or about the origin, so it's neither even nor odd. It's just nothing. If it's symmetric about the x-axis, it is also neither even nor odd. So how do you test a function without graphing it to see if it is an even or an odd function? Well, let's figure it out by working some examples. So let's look at this first one. G of x equals x to the third minus x. I want to decide if it's even, odd, or neither. So what I'm going to do is I'm going to solve this for g of negative x. In other words, for every x I see, I'm going to plug in a negative x minus x. Oh, excuse me. I did that wrong. See, I'm keeping the wrong things in there so you can see that I make mistakes and I correct them, because if you make the same mistakes, you can correct them too. I needed to plug in a negative x for this particular x here. And then I'm going to simplify it. G of negative x equals negative x to the third is the same thing as saying everything in parentheses raised to the third power. So it's negative 1 to the third, which gives me negative 1, and x to the third, which gives me x to the third. So I end up getting a negative x to the third. And I'm also going to get the negative of negative x, which is going to give me positive x. Now I'm looking at this. How does this relate to x to the third is negative x? Well, do you see that every sign is opposite? And if every sign is opposite, that means that it's got to be an odd function. In other words, I could factor out a negative 1 here, and I would be left with x to the third minus x, right? So up here, if you look at this pink, where it says an odd function, f of negative x is equal to the opposite of f of x, well, this is true. F of negative x, when I simplify it down, is the opposite of the negative 1 times the entire function of x to the third minus x. In other words, I can rewrite this as negative of x to the third minus x. That is the opposite, or if every sign is opposite, then it shows me that it is opposite, therefore it is an odd function. Now let's look at h of x. I do the same thing here. Every time I'm testing for even and odd, I put a negative x in place of every x I see. Negative x squared plus 1. And when I simplify this, negative x times negative x gives me positive x squared, right? So I have x squared plus 1. So h of negative x simplifies down to x squared plus 1. And that's what I started with. And so if I get the same thing I started with, I know that it's an even function. If I get the exact opposite of what I started with, I know it's an odd function. And then the last one, let's test this one. F of negative x. So I replace every x value in here with a negative x. Negative x to the third ends up being is negative x times negative x times negative x, which is in the same thing as saying negative 1 times x to the third. There's no x value to change this, though, so that becomes negative 1. Is every single value, every single term in this equation the opposite of the term in the original? It is not. My negative 1 has stayed the same. Therefore, it is neither even nor odd. It is neither. Okay, these are the examples that they gave you in the book. They worked them out the same way I did. You can look at them again. You can also graph them and see the graphical solutions if you'd like. But that is how you test for whether a function is even or odd. Hopefully you have enough to do your homework. There are going to be a couple of problems that I did not go over exactly how to do, because I want you to see if you can figure out how to apply what you've learned. If you have questions, again, circle the problems. Check your work at home, but circle the problems, and I will give you the answers in class, the worked out answers in class, and we will go over anything you didn't understand. Hope you have a great weekend.